Hey guys, we're back at it again with another walkthrough video. This week we're going to be working on how we can use logarithms to solve equations. Let's get started. Okay guys, so most of my grade 12 students are now at the point in their math courses where they're dealing with exponential functions, which they learned about in grade 11, but now they're also learning about the inverse of an exponential function, which we call a logarithmic function. Most of my grade 11s have learned how to solve exponential equations. However, they were only able to do so if the bases were the same. And what I mean by that is this. Let's say I had a question such as 2 to the power of x plus 1 is equal to 8 to the power of 2x minus 4, let's just say. So what you learned how to do in grade 11 was you learned that, well, if the bases on either side of the equation are equal to each other, that must mean that the exponents are equal to each other as well, which makes sense. If I have a to the power of x equals a to the power of y, well, if a is the same on both sides, this equation will only be true if x and y are the same thing as well. So the main intuition behind solving exponential equations in grade 11 was make the bases the same on either side, then the equation is pretty easy to solve from there. So in this case here, what we would do is we would recognize that 8 is actually a power of 2. More specifically, it's actually 2 to the power of 3. And then what we can do from here is I know there's a little exponent law that will allow me to simplify this a little bit more. I know that if I take some base raised to some power, and then I raise that base to another power, I know that these exponents actually multiply to each other like this. So I can use this rule to change this up a little bit. So I can take that 3, which is kind of acting like the a in this case, and I can multiply it by the 2x minus 4, which is kind of acting like the b. I just got to remember, because my 2x minus 4 is multiple terms, I need to package it inside of a bracket. All right, and now we get to a little situation like this. Here we can see that the bases are the same on both sides. We have a 2 here and a 2 here. So given this rule here, if the bases are the same, the exponents must be equal to each other as well. So I can just kind of forego the bases and just completely start working with the exponents. And then from here, I'm just solving a simple linear equation, stuff that we've been doing since grade 9. I can just get all the x terms onto one side by moving that over there with an opposite operation. And I can get all the constant terms to the other side, moving that 1 there with an opposite operation. 1 minus 6 is -5. -12 minus 1 is -13. Then we can just easily divide both sides by 5. And we get that x is equal to 13 over 5. So this is how you guys are solving exponential equations in grade 11. However, sometimes things don't work out so easily, and sometimes we can't make the bases equal to each other at all. So if that is the case that we run into, we have no choice but to use logarithms to solve exponential equations. So let's do an example like that. And I'm going to pick a very difficult one just so we can kind of show all the steps possible and as many algebra steps as we need to. All right. So let's say I had a question like this. Let's say I had 7 to the power of 2x minus 1 is equal to 5 to the power of 3x plus 4, let's just say. Okay. So over here, we have a base of 7 on this side and a base of 5 on this side. 5 is not a power of 7. 7 is not a power of 5. So there is no possible way we can make the bases the same like we did in the last example. So we're going to have no choice here but to use logarithms. So what I can do to an equation is I can take mathematical equations such as these and apply functions to both sides of them, which is no different than me adding something to both sides or multiplying something by both sides. I can basically apply functions to both sides as well. And that's exactly what I'm going to do here. What I'm going to do here is I'm going to apply log to both sides. So that's going to look something along the lines of this. I'm going to log this stuff here. And again, it's completely fine if I apply a function to one side of an equation as long as I do it to the other side as well. All right. So from here, the big kind of issue is when we were making the bases the same, we were kind of able to take our variables, which are kind of trapped in the exponents, and we were able to bring them down into the main equation. That's kind of what our goal here as well by applying logs to both sides, because you guys learned this little log property here, or at least you should have learned this log property here. If not, I'll go over it quickly. If you have a log of some base, and then you have, I like to call it the log operator in here. If that operator is raised to an exponent, what I'm actually allowed to do is I'm allowed to drag that exponent to the front, leaving me with something like this. And that's exactly what I can do to both sides of the equation here. I can take the exponent on the log operator and kind of package them like this, and I can drag them down to the front of each log, which will get these guys from the exponents down into the main equation, which is exactly what we want. So I'm actually going to do 2x minus 1 times log 7 is equal to 3x plus 4 times log 5. And just kind of notice how I package these guys in a bracket such that when I bring them down, I'm making sure that I'm multiplying the whole expression by the log value. Now from here, believe it or not, I just have an easy linear equation to solve again. I can just treat log 7 like any constant, and I can use distributive property to simply expand this stuff out. So I'm going to multiply log 7 by the 2x, which is going to get me 2x log 7. And then I'm going to multiply the log 7 by the -1, which just gets me negative log 7. I can do the exact same thing on the other side. That's going to get me 3x log 5 plus 4 log 5. Yep. Now, very similarly to how we usually solve linear equations, I want to get all my terms with the variable I'm trying to solve for on one side, and then all my constant terms onto the other side. So I'm going to very simply I'm just going to drag this 3x log 5 term to the left with opposite operations, and this minus log 7 to the right with opposite operations. So that's going to get me 2x log 7 minus 3x log 5. And that's going to equal 4 log 5 plus log 7. All right. From here, we got to remember our factoring techniques. Because the problem here is usually in a simpler linear equation, I would just be able to add these terms up by combining like terms and adding or subtracting the coefficients in front. However, these terms are a little bit more complicated. It's kind of tough for me to add 2 log 7 and then subtract it by 3 log 5. So what I can notice is that both of these terms have a common factor. They both have a common factor of x. So I can take out that x, and then in a bracket, I can write down what these two terms would be if the x wasn't there. So if I take an x out of 2x log 7, all I'm left with is 2 log 7. And if I take an x out of negative 3 log 5, all I'm left with is negative 3 log 5. And then that's going to equal what I have here. Now, finally, all I have to do from here is just divide all of this stuff to the other side of the equation, and then voila, x will be solved for. So it's over 2 log 7 minus 3 log 5. This guy looks kind of messy, but believe it or not, this is the exact value answer to this problem. If I wanted to find an approximate value, I could use my calculator. So using my calculator, just hang on a second, guys. I'm going to figure this out. The easiest way to do this is you should be able to be using a calculator that will essentially let you plug all this information in at once, such that your calculator screen looks identical to your piece of paper. However, if you don't have that, there's nothing wrong with breaking this down into smaller steps using BEDMAS. I'm going to use my good calculator and calculate this thing flat out by typing it in exactly as I see it. And when I do so, I get a value of negative 8.log5. I encourage you guys to do the problem as well to see if we get the same thing. And we call this guy an approximate value because we rounded him slightly and actually calculated him in our calculators. And that's how you solve a more complicated exponential equation using logs. Well, guys, there you have it. Hopefully now you understand how you can use logarithms to solve exponential equations. If you have any more questions about problems like these or want to learn more, book a session with us now. We have amazing options available to help you stay ahead of the curve. Take it easy, guys.